Welcome to this explainer. I am literally so incredibly excited to be here with you today because we're going to explore something truly magical, the fundamentals of robot motion. We'll be unpacking exactly how engineers take the graceful, intuitive movements of biological life, like just the simple sweep of an arm or the complex grasp of a hand, and translate them into these rigorous, precise mathematical models that machines can actually understand. It's this absolutely fascinating bridge between the natural world and mechanical engineering. Okay, let's dive into this and take a quick look at our roadmap. First up, we have the anatomy of motion. Then we'll tackle forward and inverse kinematics. Third, we're shifting frames of reference. And finally, the unified motion matrix. I assure you, we are going to build this up step by step, going from the super intuitive movement of our own bodies all the way up to complex mathematical coordination.
So, starting off with Section 1, Anatomy of Motion, from bone to steel, it's time to marvel at the ultimate engineering blueprint. Whenever engineers actually set out to build a robotic arm for a specific task, they basically look right at us. Our bodies are just incredibly sophisticated mechanical systems, and deeply understanding them is the absolute first step to mimicking their utility with steel, wires, and motors. To really appreciate the monumental challenge engineers face here, I want you to look at this number, 23. There are 23 independent motions, or what roboticists actually call degrees of freedom, in the human hand just distal to the wrist. No way, right? But it's true. Every single digit except your thumb has 4 degrees of freedom, accounting for the joints in your fingers and their side-to-side abduction. And the thumb itself, thanks to its complex evolutionary design, it boasts 5 degrees of freedom all on its own. Replicating this staggering biological wonder is just a massive, massive task for anyone building a robotic hand.
And hey, the complexity totally doesn't stop at the hand. Let's say we exclude the hand for a second and just look at the human upper extremity. We've got 7 distinct degrees of freedom going on. Try it out with me. You've got your shoulder pitch and roll, the yaw of your arm, the pitch of your elbow, and finally, the pitch, yaw, and roll of your wrist. Those 7 specific independent motions are exactly what allow you to position your hand precisely anywhere in 3D space. Grounding this concept right in your own body is honestly the absolute best way to intuitively grasp the technical concept of degrees of freedom. It's simply the number of independent variables you need to completely define a system's physical configuration.
So, how do we take our squishy human biology and map it over to robotic engineering? Well, we have to look at how robots physically mimic these movements. Enter the revolute joint. This is a physical connection providing exactly 1 degree of rotational freedom. It operates pretty much exactly like a simple hinge on a door, just opening and closing along a single axis. It is the absolute fundamental building block for a ton of classic robot arms out there. For instance, the famous Puma 560 robotic arm pulls off its wonderfully fluid motion by utilizing exactly 6 of these revolute joints connected in a sequence. But, not all mechanical movement is about spinning or rotating. We also have what's called a prismatic joint. You can kind of contrast the turning, angular motion of a revolute joint with the straight sliding motion of a prismatic joint. This one provides a single degree of linear freedom. If you imagine, say, an antenna extending outwards or a drawer sliding open on its tracks, you're perfectly visualizing prismatic motion. And then we get to the real powerhouse of joint connections, the spherical joint. This is a highly complex connection that allows for 3 distinct degrees of rotational freedom, all happening right at a single point. If you want to visualize this one, just roll your own shoulder around. Yeah, the human shoulder acts very much like a spherical joint. And let me tell you, from an engineering perspective, building and then mathematically controlling a joint that manages multiple rotational axes intersecting all at once, that is a tremendous, tremendous challenge. All right, that brings us to Section 2, Forward and Inverse Kinematics, the two-way street. Let's shift our focus to the math. Now that we understand the physical joints themselves, we need to look at the mathematical frameworks required to actually command these physical components to move. Because, let's be real, having the shiny hardware is completely useless if the software doesn't know how to drive it. Now, what's really interesting about this slide is the contrast between the 2 main problem sets in robotics. Forward kinematics is basically all about figuring out where the robot's hand currently is. Like, if you were given the exact length of every link in the arm and the exact angle of every single joint, you can easily calculate the final XYZ position of the hand. But inverse kinematics? That works completely backward. It's figuring out how to get the hand there. You start with the desired XYZ position in space, and you have to do the math to calculate the precise joint angles required to actually reach that spot. Let me break down why understanding inverse kinematics matters so much.
It is literally the fundamental key to path planning. Let's say you want a robot to simply reach out and pick up a cup from a workbench. The computer already knows the target location of the cup, sure, but to get the robot arm to safely move its gripper to that tool without crashing, the system has to continuously solve inverse kinematics over and over again to plan the exact precise angles for every single joint along that desired path.
Which leads us right into our third section, shifting frames of reference, the math of space.
To actually pull off all this path planning, we need to guide the computer in mapping out the three-dimensional space the robot operates within. Engineers do this by attaching a coordinate frame, your classic X, Y, and Z axes, to the base of every single joint. Moving from one joint's reference frame to the next involves shifting those frames sequentially. Typically, it's done in two distinct steps. Step 1, you translate or slide along a path. Step 2, you rotate by a specific angle. And I absolutely must strictly emphasize this because it trips up almost every beginner. The order matters, big time. A translation followed by a rotation mathematically yields a completely different final position than a rotation followed by a translation. The math is incredibly sensitive to the sequence of those movements. That strict sequence brings us perfectly to our final section, the unified motion matrix, translating the code. You see, since a robotic arm has multiple joints, calculating the translation and rotation step by step for every single tiny movement gets incredibly complicated and computationally heavy. Engineers needed an elegant mathematical tool to just bundle these complex sequence steps into manageable calculations. Enter the homogeneous matrix, commonly denoted simply as H. Without getting bogged down in the matrix algebra here, you can basically think of the homogeneous matrix as a universal set of mathematical instructions. It elegantly unifies both the translation and the rotation into one single neat block of code. By multiplying these matrices together, it tells the robot precisely where a specific joint is located relative to its original base frame in 3D space. It literally turns a logistical nightmare into clean, executable math, a total game changer. But of course, to ensure everyone generates these matrices exactly the same way, the engineering world relies on Dennevit-Hartenberg, or DH parameters. These are 4 highly standardized values used by engineers to systematically align and attach coordinate frames across multiple robotic joints. Basically, you can view the DH parameters as the absolute rulebook for linking the math of one joint to the next across a robot's entire physical structure. It ensures that no matter how many joints the robot has, the underlying coordinate math stays totally consistent.
Now, I know simply reading the definitions of parameters can sound a bit dry, but check out this visual approach for understanding the parameter A. Visualize the link parameter A as an expanding cylinder whose axis is the z-axis, expanding until it just touches the next joint axis. And this brilliantly illustrates how engineers bridge that tricky gap between abstract math and physical reality. It's an evocative, almost sketchbook-style visualization that makes the completely abstract concept of a DH parameter feel physical, intuitive, and honestly, easy to grasp.
Wow, we have covered a lot of ground today. We've moved from the biological anatomy of our own joints, through the forward and inverse kinematics that actually drive these machines, all the way to the unified matrices that calculate space itself. It leaves us with a truly provocative thought to end on. As we continue teaching metal to mimic biology with ever-increasing mathematical complexity, how long will it be until these matrices can perfectly replicate the 23 degrees of freedom and the absolute grace of the human hand? It's a wildly thrilling frontier, for sure. Thank you so much for joining me on this explainer, and I really hope this sparked your curiosity to learn even more about the future of robotics.